Hi, everybody. Oh, that's loud. Hold on. I must have bumped that. Oh, or the mic's just right in my mouth. There we go. Alright, welcome back to Chem 121. We have an extra lecture today, just because I want to get through all the material and not leave you guys stranded at the end. Like, oh, well, chapter 10, guess we didn't get to it, because we went a little slow. No, we'll just tack on an extra day here. That's fine. We're going to talk about equilibrium today, and all sorts of equilibrium things. That's what Le Chatelier's principle is. And then we're going to do a little bit of Chapter 10. We're going to talk about what acids and bases are. Just enough to ensure that in the next 2 days that we have next week for week 10, that I can finish all the content. Okay, announcements down at the bottom. Quiz 7 and lab worksheet number 4 close tonight. Make sure you get those in if you haven't done so already. Quiz number 8 is due on Monday. It'll close Tuesday. After we finish this chapter, which will be today, quiz number 9 will close, or sorry, it'll actually be due Tuesday and close Wednesday. So that on Thursday, you'll have a chance to review it for your exam on Friday, because Friday next week is midterm number 2. And then immediately after that, sometime the next week, whatever time I put on the syllabus, I don't know off the top of my head, will be the final exam. And we'll have a review session during finals week on the date posted in the syllabus. Though you can always ask me questions over Discord if you'd like. I'm available all through finals week. All you do is just ask questions either through direct message or in the chat, and I will do my best to answer them. All right, let's talk about equilibrium. Equilibrium is one of these concepts that's very difficult to get a grasp on until you actually do, and then it totally makes sense. So what I'm going to try and do is I'm going to try and explain this from multiple different angles of approach, and hopefully one of those will stick as I throw these ideas at the wall being you. So I'm not clicked on the right thing. There we go. All right. It turns out that all throughout the quarter, we've treated every reaction as doing something like is shown on the screen here. Let's suppose I have HCl reacting with water, and you're going to see this weird thing that I've written here. Like this right here. Don't worry about this too much just yet. Just accept that this is a thing that can happen, because it actually does. We have not talked about reactions with water to form hydronium yet, because we haven't talked about acids and bases. So this is a thing that happens. Now, as written, this reaction would imply that if I drop HCl into water, that over time I would end up with a beaker full of H3O plus and Cl minus, and there would be no HCls left at all. Assuming that HCl is the reactant that I have a limited quantity of. And so if I looked in the beaker at some later point, this is what I would expect to see. Absolutely no HCl should be left. It should have all reacted. That may take time to do, and how much time it takes is dependent on kinetics. But for our purposes, that isn't important. Eventually, it will hit 100% of this stuff is H3O plus and Cl minus, and there's no HCl left that you can find. But it turns out that this reaction is by far in the minority. Most reactions do this sort of thing. And you'll notice that the big difference here is that there's an arrow that goes in both directions. This is the reaction between acetic acid, or vinegar, and water. And because acetic acid is an acid, it also makes hydronium, and then the acetate ion is what's left over. Now, if this followed the same sort of principle of like reaction and then creation of products, without the reverse arrow, everything would just get kind of bottlenecked in the product side, and you wouldn't have any reactants left. But if I look at this reaction mixture, this is actually what I observe. Some half a percentage point of my starting reactant actually reacts. The remainder doesn't react at all. Or does it? Because it seems weird that such a small amount would react. What is actually happening is that everything will react, but very slowly. In reality, what's happening is some of my reactant will turn into the product. But the likelihood of these two things encountering each other and reacting is extremely high. And what happens when you make an H3O plus and an acetate ion, and they interact with each other, is they combine, and you get back what you started with. So the reverse reaction is possible. Isn't it, Maya? She's right here. Say hi. No, she doesn't want to say hi. Maya, you have something in your eye again. Hold on. Maya has very goopy eyes. Let me just get this out of your eye here. So every so often I have to, like, brush the goop out with a Kleenex. And if you think that's disgusting, well, don't own a pet. There are lots of disgusting things about pet ownership. So this is kind of like a loop of reactions. That's exactly what it is. So I turn products into reactants, and then I turn those reactants back into products, and those products then turn into reactants again. And this keeps going over and over and over forever. There's no end point to this. And so anytime I have reactants, they can turn into products. But anytime I have products, they can also turn back into reactants. Which one do I end up with more of? It depends on which side is more reactive. The more reactive side is going to push in that direction more than the less reactive side. Now, because these numbers as shown, on the left I have, this is just 99.5% of my stuff, and this is 0.5. This is the more reactive side. It's more reactive because I have less of this. It gets pushed in this direction more than it gets pushed in this direction. A good way to think of this would be kind of like if I had like a waterfall that was multi-tiered or something like this. So here's my water. It's rushing over, and it's going to pool in here. And then it's going to start trickling over. And I would hit some level of water where it would just continue to trickle over. But this level would not go up or down anymore. It would go up initially, but then I start losing water at the same rate that I am gaining the water, right? And once I do that, I will reach some equilibrium height. So my water rushing over the edge into a pool, initially, the water doesn't spill out. I'm just collecting water in the basin. But once that fills up, it starts to spill over the other brim on the other side too, and the level of water inside remains constant. Because for all the water I'm adding in, it's now brimming over the other side. With chemical reactions, it's sort of the same principle. What's happening is I'm creating products, but at first I can't create reactants because there are no products, right? And as I start to populate the product side, the potential for them to react and turn back into reactants grows until I reach an equilibrium. In which case, every time I create products, two of my products will then bonk into each other and create reactants again. And that speed equalizes. And that's what's known as equilibrium. We're going to call any reaction capable of equilibrium reversible. Something is reversible if the forward reaction and the backwards reaction, or reverse reaction, are both possible. In some cases, the reverse reaction is impossible. The reasons for this are kind of beyond the scope of this class, but they involve things like the products are very stable, or the products are very low in energy. Like, when you create them, you create like a solid. It's hard for a solid to then redissolve back into whatever it was before because it's a solid. It's all attracted to itself, right? Things like that. If the reverse reaction is possible, then you can and do form an equilibrium. And we represent that by drawing this double arrow. Now, most texts will draw the double arrow where they're both the same length. Some texts will try and draw one of the arrows smaller than the others. Is it possible for two sides of the reaction to be equally reactive? Absolutely. So if I had A plus B turns into AB, but it's reversible, if they were equally reactive and I did an analysis, then I would just have 50% on each side. So in this case, they would be completely equally reactive. I'm just as likely to have AB as I am to have A plus B separately. Would anything happen? Absolutely. So these this is the first common misconception that happens with equilibrium is it's not like everything stops, because remember that molecules are always moving, right? And so when reactions occur, they occur because things bonk into each other, and it's productive for them to react. Like, oh, I reacted two of the reactants together, so they do so. Now, even when you hit equilibrium, your reactions keep going. But what's happening is that this reaction is happening at the same time as this reaction and in the same quantity. They have the same rate. Now, the amounts that are present can totally vary. It's not going to necessarily be 50-50. In fact, 50-50 is extremely rare, it turns out. Most reactions that we're going to study in the acid-base section, particularly acids, tend to favor the reactants, and so you end up piled up on this side because you have tons of it over here, and you have very little of this side. Maya, I'm trying to teach. Maya. Okay. Sorry, I'm trying to get her to, like, not harass me. Alright. Now, I have a few pictures of this that are going to come up, but the description that I'm going to give for you is that the forward reaction will make products, and the reverse reaction will turn the products back into reactants. And as these happen at the same speed, that instance is where we reach equilibrium. So keep this in mind. It's about the speed at which the reactions occur. And speed is dependent on concentration, because we just said that in the kinetics lecture yesterday, right? If you have very little of something, things go real slow. If you have tons of it, they go real fast. Eventually, you reach the point where you have the correct amounts to go at the correct speed for both sides. And because they're different reactions, that won't necessarily correlate to the same amount. All right, we're going to show that in this picture here. So we're going to do this reaction. Hydrogen plus iodine makes HI. Hi. At the start of the reaction, all you have is H2 and I2. So nothing is reacted here. I have 100% products, or I'm sorry, 100% reactants and 0% products. After I allow a little bit of time to pass, some reactants will produce products. And what I'm going to do is I'm going to try and draw this like a graph. We're going to draw this graph on the next page, but that's not a good spot for it because I have clocks that are going to appear there. We'll try and draw it here. So time, and then amount. And so the amount of so this red line will be H2 and I2. And this blue line will be HI. Now, initially, I have lots of them, and as I react to them, I start to lose reactants, right? I will use them up. since I have no products at the start, I start to produce them. And I start making them. Now, eventually, the speed at which I'm going to make my products and use up my reactants will slow down, and it will become equal over time. I'm trying to draw that as a flat line, but I'm not capable of doing it with my tablet here. Same thing here. If I stop making products, the amount that I have slows down over time too. This was supposed to be more of a slope, but that's okay. Now, you'll notice that I didn't make them stop at the same amount. That's because this isn't 50-50. I'm not going to have 50% products and 50% reactants, necessarily. But what is important is that once you reach the point where the amounts that you have don't change, you've reached equilibrium. And so we can see that in these pictures here. So I'm going to count the number of HIs that I have. So here I have 4. 4 HI molecules. Are we at equilibrium? Let's let the reaction keep going. It looks like the reaction kept going and I made more HIs. So I have 8 of them now. HI. I put that mark there and I had to deal with it somehow. Let's check again in a little bit more time. And we'll count how many there are. Oops. I was holding down the button on my pen. You'll notice that there's still HI. But are these the same 8 HI that I had before? Turns out that the answer is almost definitively no. Because if these two bonk into each other, they would react to form H2 and I2. But at the same instant that this is happening, an H2 and an I2 might be reacting to form HI. And so I'm basically at equilibrium. I have these bonking into each other and these bonking into each other as well. And they happen simultaneously. And this keeps happening because the amounts that are there allow this to happen at the same speed. So the amount that I am producing of HI is the same speed at which I am using it up in the reverse reaction. Thus, the amount that you have remains constant, even if it's not the same 8 every time. I think I have another picture which tries to show that on the next slide. Let me just show that real quick, and then I'll go to that link, because that link is going to be something that we're going to test out here in just a second. All right, so you can see how the lines became constant once we've reached dynamic equilibrium. The amount of HI that I have over time remains constant. It's still being produced. It's also just being consumed at the same speed following the reverse reaction. I'm sorry. Now, again, where I draw these lines is irrelevant. So here in this diagram, I have lots and lots and lots of HI, and I have much less H2I2, which I drew as 2 separate lines. That doesn't matter. What matters is that the amount is constant. Wow, I don't know why the pen does this sometimes. Over, that's supposed to be an O, time. If I draw slowly, it seems to be a little bit better. I don't know why it's like this, but if I write hello really quickly, I get something like that. I think it might just be the number of images or JPEGs on the screen. But yeah, PowerPoint, kind of shitty, it turns out. All right, we're going to go to this picture here, or not picture, but there we go. This link here. I actually have given you the link for this if you want to play around with it. I got to find it in my slide here, though, because I had to actually copy it myself. All right, so let me paste this into my browser. which it won't return a error or a bug because it's not fucking YouTube here. So, all right, so I'm going to hit play. So run the browser compatible version. This all used to be JavaScript, and JavaScript is not a thing that like most browsers support without like changing a bunch of add-ons and stuff. So, all right, so I'm gonna do this. All right, we're gonna put this on the screen here. We'll put the entire simulation here. All right. So what this is going to be a simulation between A and B, where A is a reactant and B is a product. We're going to simulate that based on the position of where the molecules are in the container. What I'm going to do is I'm going to drop 10 molecules of A, and they're just going to bounce around. And over time, the count of how many molecules I have will change. Now, logically speaking, where do you think all of the molecules are going to get stuck at over time? And hopefully you're thinking, oh, they're probably all going to end up in the bin on the side marked B, because it's lower. It's a lower well, right? Now, the balls that are on the screen will bounce around, so they will occasionally bounce back. I'm seeing if one of these will bounce back while we're watching it. But we would expect that for this configuration, most of the molecules would get stuck on side B, but not all of them, right? Maybe like 1 in 10 would remain, and maybe only for part of the time. But we would reach some equilibrium where the amount on both sides remains constant. So what we're going to do is we're going to just throw a bunch of these in here. But here's what we're going to do. You might have noticed that this thing right here and this in the middle... Can I move this? There we go. You might have noticed that this blue curve looks an awful lot like the energy diagram we drew yesterday, didn't it? Where we had reactants on one side and then the products on the other side, and then we had this activation energy hump in the middle. And that's exactly what this is. Equilibrium is dictated by where I put these levels and what I do with this activation energy. If I had a reaction like this, where everything was flat, I would be 50-50, right? All of my molecules would just be equally distributed over this. But by doing something like this, I'm more likely to see my molecules on one side than the other. And if I put a giant barrier between them, I'm more likely to trap them on the side that is lower. Anything that gets over to the lower side is probably going to stay there. The lower this hump is, though, the more likely things are to come back. So what we're going to do is we're going to set up something like this. And I'm going to put a ton of these in here. So I'm going to hit reset, actually. And I'm going to drop 100 in here. There they go. Well, I gotta hit play, but there we go. So there's 100 things. And they're going to bounce around. And we're going to check on this, because I'm just going to let this run. So I'm going to hit this timer here. And we're going to let this run for a while. And when we come back and check on it on occasion, we'll notice that we're currently not at equilibrium, because the amount on both sides is not staying relatively constant over time. But eventually we will. So currently we're at 87 on the left and 13 on the right. We'll come back to that in a little bit. And we'll see how it's changed. And we'll see if we can hit equilibrium before the period is over. All right. So let's summarize the gist of what equilibrium is. For a reaction that's reversible, reactants can convert into products, and the reverse reaction of products converting into reactants can occur. The link is right here. So I'm going to paste that in the chat. Run whichever version works. If you have JavaScript enabled on your computer and you trust it, you can click that. Otherwise, you can use the simulator. And you can just play with it however you want to. But if you let it run long enough, you will eventually hit an equilibrium. And it does a remarkably good job of doing this. Equilibrium, by definition, occurs when the speed of the forward and the reverse reactions are equal to one another. What that means is that for our little example that we have going on, which I'll highlight in just a second, for this demo here, oops, I lost the thing. Oop, there it is. What that would mean is that the same number of balls are going from left to right as they are right to left. And you can see as I get more of the balls on the right side, one occasionally comes back over to the left at the same time as one occasionally pops over from the left to the right. And so I will hit equilibrium when the same number are going towards the right that are coming back from the right towards the left. The other definition of equilibrium we need to have is that the amount of reactants and products remains constant over time. So if we go back to this again, we'll hit equilibrium when these numbers on the screen are roughly constant over time. So this simulation, you'll notice that this isn't seconds, it's running it faster. I'm not really sure why it does that, but once we hit a certain amount of time and these numbers remain relatively constant, like within plus or minus 2 or 3, I would say, we've reached equilibrium. Now, if you're playing with this at home, what you can also do is you can play with this heat control. If you add heat, this speeds up all the molecules and they go faster and faster and that changes equilibrium. Or you can remove heat by adding ice to it and lower the temperature, and that'll affect it in some way too. So in order to reach equilibrium, you don't want to play with this. You want to do this initially. So we're going to just let it run, and we'll see what numbers we get. So now we have 33 versus 66, or 67. We'll see if that changes later on. Now, for any reaction that gets to equilibrium, we can define its equilibrium as a number. And so this number is called the equilibrium constant, which has a variable k, specifically a capital K. Lowercase k is something totally different and has to do with kinetics, so just be careful. Don't accidentally put a lowercase k, or somebody who studies chemistry might get confused about that. The formula for determining K is really freaking scary looking. This is how you determine K. For any reaction like this, you have AAs and BBs turn into CCs and DDs. The equilibrium constant is expressed like this. If you're looking at that and freaking out and going, what the fuck is that? That's a rational response. We're not going to do that. We're not going to calculate equilibrium constants like that. Instead, what we're going to do is we're going to calculate them conceptually. We're going to sort of use math. And here's how we're going to do this. First of all the lowercase letters are coefficients. And you'll see that they represent powers. For our purposes, that means we are just going to ignore them. The capital letters, which represent the substances themselves, show up in these brackets. And what these brackets are concentrations which we express as molarity, and we did that in Chapter 8. But again, we don't really need to worry about the numbers. Instead, here's the important stuff. You'll notice that all the products show up on the top of the equation, and all the reactants show up on the bottom. So I'm going to write it like this. How many products do you have versus how many reactants do you have? And we're going to divide those together. Okay? So forget the formula. The formula is stupid. If you were an engineer, I would make you calculate it using the formula. You guys are not engineers. You are healthcare students. You're not going to be asked, quick nurse, what's the equilibrium constant of the patient's blood chemistry? Beep, beep, beep. and then the patient dies because you didn't know the answer. Like, no, that's never going to happen, right? So I'm not going to fill your brain with useless information. But the equilibrium constant value itself is relevant. I do want to talk a little bit about it. So, again, A, B, C, and D in brackets are going to be molarity, which just means how much do you have? Lots or little? And so this is how we're going to look at that. I'm going to write this at the top here. K equals products over reactants. And the way that I want to visualize this is to use this little seesaw. Now, an unfortunate consequence of this is that the increasing value of the equilibrium constant is going to be pointed downward, because I'm trying to make this look like a reaction arrow. This arrow that I've drawn is a reaction arrow. We're going to put the reactants on this side and the products on this side, because it matches up with our reaction arrow. All right. Let's do the case that you mentioned earlier. If I have the same amount of products and reactants, what does that mean? Well, if I have the same amount, that means I would have the same number, which we'll call x, divided by itself. Assuming that x is not 0, any number divided by itself is 1. So the equilibrium constant for a reaction that I have 50-50 products or reactants is 1. So what we're going to do is, I've moved this on the wrong screen now, so let me do that. There we go. So let's go over here real quick. And I just want this formula at the top. So if the amount of products that I have is equal to the amount of reactants, the value of the equilibrium constant is 1. And that should be pretty straightforward. That makes sense. If I have the same number on both sides, the same number divided by itself is 1. All right, we'll come back to this in just a second. What happens if I have way more of one thing than the other? So let's look at this example. And so again, products over reactants. If I have a big number divided by a small number, a large number divided by a small number is a big number, right? 100 divided by 2 is 50. That's big compared to 1, right? So as I make the top number bigger and the bottom number smaller, my equilibrium constant gets bigger. And if I make it to the maximum possible extent, which would be there is 0 on the bottom, what I would approach is infinity. A number divided by 0 is not defined as a number. It approaches a number that is infinitely large. So let's go over to this again, and we will include that. Oops. Skipped a letter there. So products much greater than reactants. I apologize, I've reversed them here, but products much larger than reactants, K will be much bigger than 1. We'll say large. All right, let's go back to this. And we'll do the last case. What happens when you have, and again, K is products over reactants. If you have lots of reactants but very few products, what number would you get? Well, it accidentally popped up on the screen here. I would get a small number, right? And if I went to the extreme of that, where there were no products, I would have 0 divided by any number, which is 0. Our conclusion is that the value of k can be any number between 0 and infinity, but the midpoint is 1. And so let's go back to this over here. And we'll do this last bit. So for products being much less than the reactants, k will be much less than 1. Or in other words, it will be small. And this is what you need to know about equilibrium constants. You don't need to know how to calculate them beyond recognizing that, oh, a big K, where K is bigger than 1, means there are lots of products. A K that is smaller than 1 means there are lots of reactants. And if K is 1, they're about the same. So that's the definition of the equilibrium constant, where it comes from, and that's the fast distilled version, is just this chart here. If you have lots of one thing versus the other, your K will behave appropriately in terms of how the math shakes out. Now, why am I teaching you the math? Why didn't I just give you this chart? Because most of the time, you're going to be given is K. And you'll have to interpret what K means. So you'll have to work backwards from here. And it doesn't really make much sense to just say, well, if K is a tiny number, you have tons of reactants, without doing this discussion. In chapter 10, I'm going to show you a bunch of weak acids, and weak acids universally have a K value that is less than 1. Because they're weak, they don't react very much. So we have mostly reactants. And so that's where this discussion of what is an equilibrium constant is more or less heading. We're trying to get you just to be acclimated to what this constant means. All right. Here's a good example. Remember acetic acid, how we said that the amount that was in there was like, oops, I don't know why that disappeared. It was like 99.5% this and very little of this. When I plug those numbers based on whatever their molarity is, I don't know what their molarity is because I didn't actually do this experiment. But when I do that, the number I get for K is this. And so what you would conclude is by looking at this number, your task would be to say, I gotta get the pen out. You would look at this and you would say, hey, that's a small number. Because it's less than 1. And thus, what do you have most of in the container? Well, if it's small, I have mostly this. And that's what I want you to get out of this equilibrium constant discussion is, what does K mean when it's big versus when it's small? So hopefully the discussion wasn't too confusing on how we calculate it, because you're never going to have to calculate it. I'm going to give you the K, but I do want you to know why these numbers work out to be how they do. All right, so now that you've seen the logic behind it, what I want you to do, there's our summary. So this is everything that we've said. What I want you to do is look at these reactions here, and I want you to tell me, circle the side, if you can circle the screen, circle the side that there is more of products, reactants, or is it roughly the same? Okay, I'm going to give you 3 or 4 minutes to do that. So look at these K values and tell me more products, more reactants, or roughly the same. We'll number the equations here, so you could type that in the chat. I know it's just you, Griffin, right now, but whenever you get those, type them in the chat, and then we'll go over the answers together. All right, so we got your answers, so I'll look at these numbers. So this number is written as 2.60 times 10 to the 2. That's the same as 260, right? That's a number bigger than 1, so there should be more products. Sorry, I had to cough there, and I had to mute the thing. All right. This is real close to 1. So we would say that there are roughly the same amount, but you're right, because it's bigger than 1, you'd have slightly more products than you would reactants. And then this number is just really, really tiny, so you'd have more of these over here. All right, excellent. Let me know if you have any questions. Now, if we want to calculate the equilibrium constant, remember, this is that formula, and I told you that we're not going to calculate that, so we're just going to skip a bunch of these slides. This is just showing how they're calculated, but if I measured at equilibrium these amounts, then how I would calculate this is I would say, okay, so this number raised to this coefficient. I'm going to do this once for you, and then you'll never see it again. And then these are my reactants. I only have one, so I would do this number times this number. And so I believe you should get something like 4 for this. Oh, I got 50.3. Okay. I don't actually know the... Oh, I'm thinking of some other reaction. Okay, yeah. I was thinking of deuterium and hydrogen. All right, so what this would say is that I should have mostly products. Oops. And you can see that that checks out because there's way more products than there are reactants. All right. And again, I'm not going to make you do these examples, so we're just going to skip them. But here's the homework practice for this section. You definitely want to do as many of those as you can. If you see anything that asks you to calculate an equilibrium constant, just skip it. If you see something ask you about an equilibrium constant, like is there more or less of this, those are fair game, and I will ask you those questions. But you won't see, this will not be tested on the quiz or the exam. So you can skip it. All right. That's the first bit that we're going to do. There's not really much that I can do in 5 minutes because our break is coming up here. So I'm going to say let's just take our break right now. So we'll put this on the screen. And then we'll do Le Chatelier in a little bit. And then we'll do a little bit of Chapter 10 and we'll call it a day. So, all right. I'll go turn the music back on and I'll see you in just a little bit. That was pretty close. Alright. Let me turn off the music on my end here. Did it do it? There we go. Okay. Alright. So, now that we've discussed what equilibrium is and how we can measure it with a constant, let's talk about Le Chatelier's principle. Le Chatelier's principle is, at its most basic concept, what will a reaction do if I screw up its equilibrium? And the answer is, everything tries to return to equilibrium, right? So if you make a change to your reaction, like dumping in extra reactants or something, it will try and go back to equilibrium. And so, basically, this works as a driving force to make a reaction do what you want it to do. So I'm going to show you this reaction. This is going to be our generic reaction. A plus B makes AB. And it's at equilibrium. And so we have some amount of stuff in there of A, B, and then the product AB. Now, what would happen if I suddenly added extra B? Is the system at equilibrium anymore? So let's do an example here. So I'm going to use the equilibrium constant, and I'm going to call this, let's see here. So I'm going to say that I have 10 of this and 2 of these. And so my equilibrium reaction would be 10 over 2 times 2, which equals 2.5. All right. Now I'm going to add more B to it. So instead of having 2 in the expression, we're going to instead have more than 2, because I've added a bunch. So I'm going to go like this. And that means that this is going to happen, and that I'm no longer at this number. I would have whatever 10 divided by 12 is. 0.83. Would I be at equilibrium anymore? Well, remember, it's called an equilibrium constant, right? Which means that it's not allowed to change. So my value should always be this. This is not equilibrium. So if I add extra B into the reaction mixture, I'm no longer at equilibrium. And thus, the reaction needs to move in the direction that will bring it back to equilibrium. Well, in this case, my equilibrium constant is too small that I calculated. And I need to make it bigger, which means that I would need to have less reactants and more products, right? This number needs to go up and this number needs to go down. And as a result, the reaction would move in this direction. Mathematically, that's how that works. If you don't like math, and who can blame you, we have a different way to do this. But the numbers just help us see objectively, like, oh, it's not the same number anymore, right? My equilibrium constant is supposed to be a constant, but in doing this, it changes it, right? So, how do we figure out what happens conceptually? So, if I change the equilibrium situation by changing the amount of stuff in the reaction, then what ends up happening is the reaction will then continue to react in some way so that the value of K will return to normal. K has to be the same. Now, important to note, this is at a fixed temperature. Oh no! Oh, my simulation. Oh, the tab fell asleep. I was going to check on the simulation again. Don't suspend this tab. Okay. I gotta start it back up again real quick, so hold on. Alright, so start. Alright, I gotta let that run again because it closed it. So there it is again. I had to start it over. But I tried to put it back to where it was. So, alright. K is always going to be the same for a given temperature. If I add or remove stuff, K should be the same. If you calculate it to be different, it's not at equilibrium yet. So therefore, it will react until it is at equilibrium, and then all the amounts that are inside will change. So Le Chatelier's principle basically says if you try to change the value of K, the system will continue to react in such a way that the amount of stuff that's in there will then equal K again. In other words, if you make changes to a reaction that's currently at equilibrium, then what ends up happening is the reaction tries to mitigate, or in other words, undo to the best of its ability those changes. All right, let's look at that in a practical example here. If I put in extra B, then I have too much of it. To mitigate that, I need to then consume it. So this would mitigate it. But if I consume B, I would also have to consume A and create more AB. So if I make a change, the reaction will try to undo the change by making the reaction change, undergo more reactions, basically. So if you add something, the reaction moves in the direction that causes it to get used up. So I added this. In order to use it, I need to move the reaction towards products. I will use up the extra B that was added to make more products. What if instead I added extra AB? So I was at equilibrium, now I have too much of this to be at equilibrium. So now I need to use it up, and the only way to do that is to decompose it back into reactants. That will undo the change that happened. So if we add stuff to the container, the reaction moves in the direction to move away from that change. So let's consider a reaction here. This is the Haber process. The Haber process is industrially practical for making ammonia. We like ammonia. Ammonia is used in fertilizer and all sorts of different chemical applications. So we want to make it. Nitrogen is abundant. It's in the atmosphere. 80% of what you breathe is nitrogen. So we just kind of scoop out of the air and get it. You can literally pull it out of the air. Hydrogen we can get from various sources and is very common. But ammonia, not as common because it's reactive. So we want to make ammonia. The problem with making ammonia is that the equilibrium constant for this is small. And so as a result, you get mostly reactants. You only get a small amount of products. How would we manipulate this reaction so that we would get more products? Let's just try things and see what happens. What if I were to add ammonia to my container? I'm at equilibrium and then I'm just going to pump more ammonia in. What do you think would happen? Pumping in more ammonia means I'm no longer at equilibrium, and so the system needs to undo that. So it would undo that by reacting my ammonium and creating more product or reactants, I'm sorry. So the reaction would go this way. That is indeed the opposite of what we want. So in order to make more ammonium, don't put extra ammonium in there. That kind of checks out, right? If you want to make something, don't flood your reaction with it because the opposite reaction would occur then. All right. Let's suppose we did something different. Let's suppose that we got rid of we got rid of nitrogen. I'm going to get rid of this N2. There's now a hole. Well, if my reaction is trying to use up excess things that I had in there by turning them into the other stuff, if I create a dearth of it, or a gap, or a hole, or something like that, the reaction is going to try and fill in that hole. And so what's going to end up happening is we're going to try and fill this in, and in order to do that, I have to also make this by using up this. And the reaction would go this way. So by removing a reactant, I would then consume the products to replace the reactants that were removed. So obviously that's no good either if we want to make ammonia. So let's suppose that I wanted to make more ammonia out of this reaction. What I would instead have to do is I would have to add extra of this stuff, which would then use it up to get back to equilibrium to make more of this. Or here's a more practical idea. What if as I make this, I just take it away? Because now the system's like, well, I have to replace this, so I'll just get rid of this stuff and replace it. Because you can't reach equilibrium and have your products turned back into reactants if there are no products, right? So if you just keep taking the products away as you produce them, you never hit equilibrium and the reaction just keeps going in the forward direction towards the products. So Le Chatelier's principle is just basically, oh, I'm going to do a thing. The reaction will react to that change by attempting to undo it, which is why whenever I make a change here, the opposite thing happens immediately. The next thing that we want to consider is the effective pressure. It turns out that these are actually gases. So we aren't necessarily just beholden to changing amounts. What we can also do is change things like volume, which affects pressure, right? Le Chatelier's principle tries to keep everything at equilibrium. At equilibrium, there will be some pressure, whatever the gas pressure is in the container. Remember that the pressure is going to just be the force that molecules exert on the walls of the system that they're in, right? So that's the pressure. We also know that pressure and volume equal this. We talked about that in the gas laws chapter. We also said that if I have some container that looks like this, and I change either the pressure or the volume, the other thing will change appropriately, right? And because they're indirectly proportional, if I increase one, the other one will go down, right? And vice versa. So if my goal is to keep the pressure constant at equilibrium, and I do something that changes the pressure, the system will react to that. Now, how do you change the reaction so that the pressure equalizes? Well, if I'm adjusting the volume myself, for example, let's suppose that I reduced the volume of the container. If the volume goes down, the pressure goes up, right? Because if this number gets smaller, this number has to go up for it to be equal to whatever it was before. And then we say this expression is true if I reduce the volume and the pressure went up, now I need the pressure to go down. Well, if the volume is constant and so is the temperature at this new state, I would then just need to have the number of moles go down, right? So if I could just get less particles, I would lower the pressure. So to counteract increases in pressure, so if the pressure is increased because I did something, the reaction will move towards the direction with fewer moles in an attempt to lower the pressure back to what it was. Because this action lowers the pressure, which would counteract this right here. Okay, which side has fewer moles? Well, I have 1 mole and 3 moles of reactants and 2 moles of products. So if I wanted to lower the pressure, I would turn things into products, because there would be fewer molecules in the container, and thus the pressure would go down. That's a lot of steps of mental gymnastics. So if you don't want to worry about the logic, just remember this. If pressure goes up, how do we undo pressure? Make fewer moles. What if pressure decreases? If the pressure decreases, I need to increase the pressure to undo that. So if the pressure decreases, to make there be more pressure, I move to the side with more moles. That would be the opposite of decreasing the pressure. All right, so let's do some examples here. So I have a container, and I'm going to make the container that has all of this in here. So here's all my gas in this container. I'm going to move this so that the volume is now twice its size. If I make the container bigger, the pressure goes down. Because I made the volume go up, right? Because this happened. Now what does the system try to do? It wants the pressure to go back to what it was so that I counter that, right? So if I make the volume bigger, the pressure will go down initially. To undo that, I have to increase the pressure and move toward the side with more moles. Which side is that? That's this side. So if I expand the volume, I will suddenly convert my products back into reactants to alleviate the change in pressure. All right. What if I compress the container? I make the volume be smaller. So here's my container again. Here's all my particles. I'm going to move it inward so that it's smaller. If I compress everything, so the volume went down, so the pressure increases as a result, then my system would want to reduce that pressure to counteract what I did. I would move in the direction of fewer moles. That's this way. So I would create more products. So that's a very easy thing that we can do. I have my reaction. If I want it to not be at equilibrium anymore and I want to make more products, I'll just compress it. So this reaction is done at very high pressure to get the most product possible. All right, so we have discussed changing the amount of stuff, and now we've discussed pressurizing and depressurizing our sample. There's one more thing that we can change in a reaction, and that's temperature. We can heat something up or cool it down, and that will affect the reaction too. The reason for that is because if a reaction is exothermic or endothermic, you're going to have heat in the reaction somewhere, correct? So, for example, here's a reaction that has some color coding in there. We'll talk about the color coding in a second. But if I take this cobalt chloride compound, or complex, I should say, and I add it to water, then I get this cobalt hydrated complex, HCl, and also heat. So by mixing the cobalt chloride complex with water, it creates heat, and I get this other substance in HCl. The colors are actually the colors of the substances. So cobalt chloride complex is blue, cobalt hydrated is pink. Now let's suppose that I put this in a hot bath. I'm going to just cover up the slide that I just had there. So if I add excess heat by putting it in a hot bath, what will happen to the reaction? Well, now my reaction wants to undo that change, so it's going to use this stuff up and make more of this stuff so that I cancel out what I did. Since I made more of this and I used up this to do it, the reaction would turn more blue. So if you have an equilibrium situation where the substances have some sort of color to them, and those colors are discernible, you can figure out which direction the reaction is shifting by just looking at the color. If I shifted towards the reactants in this case, the solution would be more blue than it was before, and less pink. If I shift towards the products, it would become more pink and less blue. So adding heat to this container, my reaction will have to use it up, along with HCl and the cobalt hydrate complex, and I will make more of the chloride as a result. Let's suppose that I put this in a cold bath, so I'm going to remove heat. My reaction will want to undo that change, right? And in doing so, I will need to produce this stuff, which means I need to use this up to make more heat. And so, since I'm making more of this and I'm using this one up, this would turn the reaction more pink. So we can see the equilibrium shift in action. Now, you might also be thinking, if you're thinking back to the equilibrium constant, wait a second, how are all the numbers changing if I'm adjusting heat, which is not something that's in the formula? It's not really a chemical, right? Remember how I said K is constant at constant temperature, right? Well, if I change the temperature, I change K. And so what we're doing here is totally valid because K is only a constant for a given temperature. If you add heat or remove it, excuse me, you're changing the value of K, and so you can actually see it getting more or less pink. All right. I have a video for this. I'm going to show you this video here. We'll see if this actually loads. Oh, it did load. Look at that. Okay. Yesterday in my other class, or no, it was this class, wasn't it? I was showing you all the kinetics videos, and nothing freaking worked. All right. Oh, I need to make this smaller and then also trim out the recommended videos because nobody cares about that. All right, let's look at some Le Chatelier here. Oops, I don't want any audio because I can't talk over that. Okay. I have two tubes here. And I have forced the equilibrium in one direction or the other by adding extra stuff to it, just so you can see the difference. So the pink one is the hydrated cobalt. The blue one is the chlorinated cobalt. And you know what I'm going to do? I'm going to, let's see if I can do this real quick. So we're going to go over to this screen. And if I make this really big, now I could just capture the window. And now the equation will just be on the screen the entire time. Well, provided that I make it smaller. There we go. Okay. So now you can see the reaction the entire time here. So I'm going to hit play. And we're gonna futz around with this. So the first demo that we're gonna do, we're gonna start with the pink substance, and I'm going to add the following to it. I'm gonna add a source of chloride, which in this case will be HCl. And so you can see here, I'm gonna add HCl. So what do you think will happen if I add HCl here? I'll give you a second to, oops, I'm clicking on the wrong thing here. Give you a second to think about what will happen. I'm going to add HCl to the container. That's going to wreck the equilibrium. So what's going to end up happening is I need to undo that change, right? But in order to do that, I would have to then consume heat and this to make more of these. So as a result, we're going to make more of this. The solution should turn blue. Let's see if it does. Look at that. Immediately it just turns blue, doesn't it? And there it is. All right. Now what we're going to do is we're going to add water to it. So let me go back over here and we'll clear this. I'm going to add water to it. What do you think will happen when I add water to my solution? Well, I got to use up the water somehow to undo what I did, right? I also need to use up this, and I'll make these ones instead. So I'm going to make more of this. So the solution should turn pink, and let's see if it does. If you look at the bottom, it's easier to see this at the bottom here. Once he mixes it with the stirring rod, you can see, oh, it turned back to pink. That's kind of cool. All right, let's do the next experiment here. We're going to add chlorine again by adding HCl. And so we already saw this. This is nothing new. So that isn't any surprise. But then the next thing that we're going to do, is going to surprise you a little bit, probably. We're going to add silver. What the heck? Why are we adding silver? Silver does not show up in the reaction, but silver has a very interesting property. Silver and chlorine react very quickly and form a solid that will settle at the bottom of the container. In other words, by adding silver, I am deleting the HCl that's in there. I'm getting rid of it. Because the Cl will then bond to my silver that I'm adding, and it is effectively removed from the solution. What will happen when I add silver, which removes chloride? Well, I need to undo what I just did and make replacements, right? Which means I have to reduce my reactants. So, should turn pink. Let's see what happens. Now, it's hard to really see with the white powder that's in there, but you'll notice that after they stir it and let the powder sink to the bottom, it's definitely less blue than it was before, wasn't it? Don't worry about the equation on the screen. There's multiple equilibrium going on there. You don't need to worry about that. The result, though, is that it turned pink. All right. It's very hard to do the pressure example with this because these are liquids, and pressures don't affect liquids very much. But we could totally do the temperature example. All right. Let's put this in a hot bath first. So we're going to add heat to it. What color should it turn? Well, if I add heat, I need to undo what I added, which means I got to get rid of these and produce these. So heating the solution, putting it in the hot bath, should turn it blue. We can see that when we hit play. It's not in the bath yet. It's in front of it. So we'll put it in the container. And you'll notice that the change starts at around the top where the surface is first. You can see it's getting very, very blue. Again, don't worry about the reactions on the screen. Just the stuff that I drew at the top there. All right. So now we've got that in there. It's in the hot bath. Let's do the opposite. Let's get rid of all the heat. Let's make it really cold. What color will it change? Well, I need to undo what I did, which means that I need to use this stuff up to make more heat. So it should turn pink. Let's see if that happens. This one, unfortunately, the video fades out right before it turns pink. So I'm going to try and pause the video where you can start to see that it's turning pink. You can very barely see at the very bottom of the container that it's starting to turn pink. And just as it starts to become very visible, everything fades to black, which is real unfortunate, right? But I know how YouTube works, so I can just go frame by frame until it starts to get dark, and you can see that it's definitely more pink than it was before we put it in there. So there's the initial state. There's the final state. All right. So equilibrium is a thing that happens naturally to reactions, and we can manipulate it using various conditions. And those conditions are changing the amount of a reactant or product that's in there, adding or removing heat, and in the case of gases, pressurizing or depressurizing the container. Oops, we can get rid of that now. All right. So let's do our concept check. I'm going to put this reaction on the screen here. We're going to assume these are all gases. Turns out they're not, and it turns out CS2 actually isn't red. But for the purposes of this reaction, let's just pretend it is. Everything is a gas, and CS2 is red. And I want you to answer these from the perspective of, will it be more red, or will it be less red once you have done this change? So we're at equilibrium, and the solution is kind of red. It's not intense, but it's not clear and colorless, okay? All right, so change number 1, I'm going to add H2S. Change number 2, I'm going to remove CH4. Change number 3, I'm going to make the solution cold. And change number 4, I'm going to compress the system. So what I want you to do is tell me, for each of these 4 changes that we do, more red or less red. I'm going to give you 5 minutes to think about it. Do exactly what I've been doing. So for this first one, I'm going to add this. What should you do to counteract that? And how does the reaction change? All right. I'll go silent for a bit and let you think it out. Good luck. Oh, I don't have to wait any longer for people to work on this because there's just one person watching. So, all right. So, let's go over the answers here. So, we're going to do all of these from the perspective of CS2. And I want it to be more or less red depending on what we're doing. So, we're going to look at this. Okay. So, for number 1, I'm going to add more H2S. So, I'm going to put more in the container. And I have to undo that change. That means I need to use up the H2S that was there and some CH4, and I will have to consume some heat, and that will make more products as a result. So by adding H2S, the reaction then consumes that H2S to produce more CS2, which means more red. All right, let's do that again for the next one. I can click on this thing. Okay, I'm going to remove CH4. How do I fill in that gap? I need to produce it again to undo what I did. And in doing that, I would also need to produce more H2S and heat. In order to do that, I have to consume CS2 and H2. So this would become less red. All right. Number 3, I want to make the solution real cold. So I need to make this cold. There will be less heat. I need to replace the heat that was lost. And in doing so, I will also create more H2S and CH4 at the expense of these over here. So this would become less red as well. All right. Finally, number 4, if I reduce the volume of the vessel, the pressure will go up. I need to undo that change. So to make the pressure go down, I need the side with fewer moles. Which side is fewer moles? So I have 1 plus 2 is 3 versus 1 plus 4 is 5. 3 is less than 5, so the reaction will move in that direction, which means I'm going to have less red because I'm moving away from CS2. All right. One last thing I want to mention is that when we describe these reactions, a way to describe how the equilibrium shifts is to say that the reaction moves towards, and I would either say reactants. In this case, I would be moving towards the reactants. Another thing that you could also say is that it would be moving toward the left. So this is something that might be asked on a homework question. Which direction does equilibrium shift? For number 4, it would shift to the left because we're moving towards the reactants. Likewise, if I had something that was moving in the forward direction as opposed to the reverse direction, we would say that this reaction is moving the products or the right. All right. That's equilibrium. And that's Le Chatelier. And also that's why we had to spend an extra day, because it's complicated, right? It takes a while to get your head wrapped around this topic. All right. I think that that's the end of the chapter. Is there homework practice at the bottom? There is. Okay. I've written all over the slide. You can pause the video and go back and see what that is. But there's the homework practice at the bottom there. And then we have our hooray orc right here. Hooray! All right. We have 10 minutes left. We can do a little bit of chapter 10. If I can find it in the folder here. There it is. It's the last chapter. So let's do this. Oh, by the way, if I wanted to go back to my, this thing, I think it might be at equilibrium now. The numbers are cut off, though, so we'll just do that. So what do we got? About 27 or 26 or so, and about 73 or so. And it's just been like, I checked this like 10 minutes ago, and it was at these numbers too, so we're going to be at equilibrium here pretty much for the rest of the time. I'll check back on it in 10 minutes, I guess, right before we end class. All right, this is the last chapter. So just these sections are left for us to talk about. And then we're done with Chem 121. You're done with Chem 121. I'm never truly done with Chem 121 because I teach it. I'm teaching it next quarter. I'll be done when I retire. You'll be done after this chapter. And the final, I guess. All right. Chapter 10 is all about acids and bases. Acids and bases are a very common category of reactions that we study in chemistry and also in biology and physiology. Acids are real important to you because, one, your stomach is full of them. Your stomach is full of the equivalent of like 0.1 molar HCl. And secondly, acids and also bases cause different physiological compounds to denature. For example, proteins are only able to function within a given pH range. If it's too acidic or too basic, they denature and they unravel, and that's bad. Things like your blood are maintained at a very specific pH. If you stray from that pH too much, you undergo what's called acidosis or alkalosis, I believe is your pH is too high. And you very quickly die if your pH is off by too much. And this can happen if you have way too much CO2 in your bloodstream and not enough bicarbonate buffer, for example. So we want to study all this because obviously you don't want that to happen to you. But in medicine, it's important to have an understanding of what pH is and what acids and bases are. So we're going to start with just some generic definitions here. What are acids? Acids have the following properties. They taste sour. This is a picture of someone who ate something sour. Ugh. Acids are also capable of dissolving metals at high enough concentrations. Not all acids are strong enough to do this. If you put a penny in vinegar, it might slowly corrode. If you put a penny in nitric acid, it corrodes like crazy. But they all have the potential to be corroded by an acid. There is a substance called litmus paper that detects acid. Blue litmus paper will turn red in the presence of an acid. Red litmus paper will remain red. And then the final property about acids that we care about is that acids and bases neutralize each other. So an acid and a base will react to do interesting things. We'll talk about that next week. We just want to define what these things are. Where do you use acids? Acids occur naturally in things like fruit. So you've heard of citric acid, right? You've also heard of acetic acid or vinegar. That's not a fruit, but it is something that we use in things like cooking. Other industrial purposes or industrial uses for acids include things like sulfuric acid, which is used in car batteries. Hydrochloric acid is also very important for various applications. One of those is it's more or less what's in your stomach. Is this my table of acids? Yeah, here we go. On this slide are a bunch of different uses for different acids. My particular favorite is carbonic acid, which is what is in Polar Seltzer, which is what I'm drinking right now. Carbonic acid is simply just CO2 reacting with H2O. And I'll write that reaction down for you in case you're curious. And it is in fact an equilibrium. So if you add pressure of CO2 to your container, we have to use that up to produce more H2CO3. Oh no, it's Le Chatelier. See, it all comes together, right? So if you want to make carbonic acid in your water, you pressurize the heck out of your soda bottle. This is why when you open your soda bottle when it's fresh from the store, you hear this tss as the pressurized CO2 fizzes out of the container. Or it doesn't fizz out, but it just escapes the container. Because we've pressurized it so that we can increase the amount of H2CO3 that is present so that it is nice and tart and tastes good. All these other acids are common enough that they're worth mentioning, but for our purposes, it's just nice to know that they exist. Structurally, acids have the following characteristics in common. The most important one is that they have an H in them. The acid part pops off as H+. Then you have the ion, which is just whatever's left over. In what are known as oxyacids, where you have your H's bonded to O's, the H's that are bonded on your O's can pop off. These are going to be your H+. Same thing over here. Here's my H that'll pop off. Down here, here's my H that'll pop off. These H's are not acids. Now, why does the H specifically on the oxygen pop off? And the answer is, well, if I consider the electronegativity of these, the difference between them is fairly large. It's large enough that what oxygen will do is it will just say, okay, these electrons belong to me now. And it will become O- over here, and this H+ will pop off and just float around the solution. Over here, the electronegativity difference between these two is not large enough for that to happen. So the H remains covalently bonded to the carbon. I'm going to hit clear on the ink because the last thing I want to indicate is that if you see a group like this in a molecule, this is what's called a carboxylic acid. Carboxylic acids are acids because it says that in the name, but functionally this COO with a minus charge is very stable. And the way that I make that stable is by taking these electrons back and producing H+. So this is a very common functional group that you're going to see in organic chemistry. All right, so those are acids. Let's do bases. What are bases? Bases taste bitter. It's the same person. She just doesn't learn. Things that are bitter are things like caffeine or what are common bases that you eat? Caffeine's really the big one that I can think of. If you've tasted like pure cocoa, it has a lot of caffeine in it. And it's very bitter. This is where bittersweet chocolate comes from. Bases also feel slippery. This is because bases undergo a reaction called saponification on contact with fatty acids. Guess where fatty acids can be found? That's right, your skin cells. When you contact them with soap, a reaction occurs and they feel slippery. What does the slippery feeling caused by? It's your flesh dissolving. Yay! When you use soap in the morning or evening or whenever to shower, you're dissolving your flesh. But don't worry, that flesh is dead. I love telling everybody that story because not everybody knows that when you use soap, you're actually dissolving your skin. That's the point of it. But it's the dirty stuff that you don't want, right? So we're getting rid of it. Now, just like acids turn red litmus paper, blue litmus paper red, bases turn red litmus paper blue. Blue litmus paper remains blue. And then finally, bases neutralize acids, just like we would expect, right? All right. Bases are not common in food. The reason that I could only really think of caffeine was because that's the primary one. Bases are most common in industry and are used in things like cleaning. However, there are some medicinal uses for bases. For example, an antacid. An antacid is made of bases, particularly the bases bicarbonate or carbonate. If you eat something like Tums, Tums is calcium carbonate. Baking soda is sodium bicarbonate. And when you eat this, it reacts and neutralizes your stomach acid. Here's some common bases that are on the screen. The other purpose for bases is for cleaning stuff. Like we just said, bases will saponify fatty acids and react with them. Things that have fats and in them are things like grease or dirt or grime. So if you have like oily or grimy pans, you put soap in them to break that up. You saponify and dissolve the grease, and then you can wash it away more easily because it's more soluble in water. And I believe that that's as far as we're going to have time to get. So that's our introduction to acids and bases. You've seen what acids and bases are. When we come back on Monday, I almost said tomorrow, there's not a fourth lecture. When we come back on Monday, we're going to talk about various definitions of acids and bases. Like I showed you earlier, where we just said, an acid is an H+. It's things that make H+. So that's where we're going to go with that. Our last little check-in on our equilibrium here, you can see that the numbers haven't changed very much since the last time we checked in. So this is now at equilibrium. Things are going left to right at the same speed that they're going right to left, more or less. And if I leave this going all night, then we should come back tomorrow and see that it would be at the same thing. But there isn't class tomorrow, so I'm going to just close it, and we're never going to worry about it again. All right. But you can play with that experiment if you'd like to. All right. I want to thank Griffin for coming out to the lecture, since he's the only one that I saw in the chat. Everybody else, when you watch this later, make sure that you ask me any questions you might have, because obviously I won't be there to answer them. Make sure that you get quiz number 7 and lab worksheet number 4. Those are due tonight. They were due yesterday. They closed tonight. Quiz number 8 will be due Monday. I will get quiz number 9 online after class today. That'll be due on Tuesday next week and close Wednesday, so that it will be available on Thursday for you to see. Quiz number 10, we'll talk about it next week. It's an open quiz. It's worth 0. You could just take it and test your knowledge for the exam. That's all I got. Thanks for coming to the lecture. Ask me any questions you might have in Discord. Have a wonderful weekend.